Hello learners, welcome to session 2 of week 3, Algebra for Numbers. In this section 2, we are looking at mathematical induction. I am Munkaila Dasmani, your course instructor. By the end of this session, you should be able to state the principles of mathematical induction, identify the relevance of mathematics induction in algebra. You should be able to describe the relevance of the P-no axioms, explain the limitations of mathematical induction as a method proof. Let's look at a very simple brief story about mathematical induction. So we begin this story of mathematical induction by a renowned mathematician, Carl Friedrich Gauss, 1777 to 1855, who was one of the most significant contributors to modern mathematics. According to the story, Gauss was an elementary school student who was constantly disrupting his class, and his teacher decided to give him a task to occupy his time, and the task was adding out the numbers from 1 to 100. Unfortunately for the teacher, Gauss was able to give the answer as soon as possible, immediately. The sum 2 is 50-50, and the teacher was wondering how it came by. So let's see how Gauss did this. So this is how he did this. This is one of the ways he explained. There are 100 numbers from 1 to 100, and they can be divided into 50 pairs of numbers, each of which sum to 101, and that is, if we are going to divide them, we can start from 100, 99, 98, 97 in that order. Then he started from here 1, 2, 3, 4 in that order. So when you sum, what do you get? 101, 101, 101 in that order. So that's what he did. So and he realized that he divided into 50, and he had 101 up to 50 times. So 50 times 101, which is 50. You can use the above idea to give a very general answer to the question of how to sum numbers from 1 to n using mathematical induction. So in general, mathematical induction can be used to prove a conjecture, but usually the conjecture cannot be seen by using inductive method. Good. So definition: mathematical induction. The principle of mathematical induction is usually stated as follows. Let P of n be a sequence of statements endorsed by natural numbers. N be a member of P, and it's a natural number. So first one, suppose that P1 is true. That's the first step. Once P1 is true, so here we look from both left and right side. Once both of them are true, we call the basis step. Now, if P1 is true, then the next one is, if Pk is true, then Pk plus 1 is also true. Then we call this inductive step. If once Pk is true, we establish that Pk is true, then Pk plus 1 must be also true. So once these two conditions satisfy, then Pn is true for all n being a member of P. So you can, in some instances, say inductive hypothesis. Okay, let's see theory. Let S be a subset of P satisfying the following. 1 is a member of X, and I think we agree to that. If n is a member of S, then n plus 1 is also a member of S. Then we can say that S equals to P. So we don't give proof here, either of these versions. They are just simple. Instead, we give an axiomatic construction of the natural numbers, including the notions of addition and multiplication of such numbers. Okay, in terms of what we call the P-no postulate, that's what we are going to deal with. So the P-no postulates. The P-no postulate for natural numbers were first given by mathematician P-no 1858 to 1932 in the year 1889. I think I've already explained this in the previous section. The axioms were the accumulation of about a century of work in developing notions of arithmetic as a system of formal reasoning. Good. So let's see the P-no postulate. The positive integer P is a set with mass S mapping to P from positive integers to positive integers. call the successor map satisfying. First, there's a natural number 1 such that 1 is not equal to successor for any n be a member of P. So here we say that 1 is not a successor of any natural number. Here is it's not successor of any natural number. If successor of m equals successor of n, then we say that m equals n. If n is a subset of P such that 1 is a member of S, if n is a member of S, then successor of n is a member of S, then we say that n equals to P. We've done this already, and I think we also looked at the proof. If n is a member of P, then n is not equals to its successor. As a number cannot be its own successor. 5 cannot be its own successor. And that is, we've also established all these proofs. That is, if n is a member of P and suppose n is not equal to the successor of m, then for any m be a member of P, n equals to 1. We've also done this proof. Okay, let's see example 11. Proof summation of k equals to 1 up to nk equals n plus n multiplied by n plus 1 all on 2. So to prove this one, we start by this first basis or base step or the basic step, and the basic step says that for n equals to 1, then what do? We find our left hand side. P of 1 implies that summation of k equals to 1 up to 1, and here k, so you put 1 there, k. So what do you get? I get 1. And then we go to the right hand side. So p of 1 implies that 1 times 1 plus 1 all on 2. What do I get? I get 1. Now, since the left hand side equals to the right hand side, then it follows that p1 is true. So that's the first one. Let's go to the next. So assuming that Pn is true. We're assuming Pn is true. If Pn is true, then what happens? So we have the statement Pn plus 1. Pn plus 1 statements. Okay, so here we can say that Pn plus 1 equals 2. So what do you get? So you get Pn plus 1 equals 2. You get your n plus 1. So Pn plus 1, that is n plus 1 all on 2 plus your n plus 1. Okay, so by simplifying this, what do you get? You get n plus 1 plus 2 n plus 1 divided by 2. So you further simplify, you factor the common ones out. So you can see that there's n plus 1 here. So n plus 1 and then n plus 2 divided by 2. Okay, so n plus 1, n plus 2 all divided by 2, and that is true for p equals 2 or p of n plus 1, and that is actually true. Therefore, what can we say? So by the principle of mathematical induction, Pn is true for all n. So therefore, Pn is true for all n, because the results we obtain here is true for p of n plus 1. Good, and that is the proof. So let's look at example 12. We want to prove that this statement is true. So here let's Sn be equals to 1 cube plus 2 cube plus n cube, and they're the same as n square n plus 1 square or divided by 4. Okay, let me divide this into 2. So first we look at the left hand side. Natural number, since every natural number starts from 1, we have 1. So we can say that for n equals to 1, let's see S1. S1, we put S1 here, get 1 cube, and that equals 1. And then that is left hand side. We also have S1 equals to 1 square 1 plus 1 all square divided by 4, and I get 1. So that is this one to the right hand side. Okay, so what do we conclude? Since the left hand side equals to the right hand side and is equals to 1, we will say that P of 1 is true. Good. So P of 1 is true. So what is left? You show that the second one next. If P of n is true, that is, if P of n is true, then the statement, what will be the statement? P of n plus 1 must also be true. So let's see. S of n plus 1, this now equals to n square n plus 1 all square divided by 4, then plus n plus 1 cube. So we proceed. When you simplify, what do you get? So you get n square n plus 1 square plus 4 n plus 1 cube all divided by 4. Good. So by simplifying this, so you will get and then factorizing n plus 1 square out, and then you factorize n square plus 4n plus 4, you get n plus 1 square and then n plus 2 square all divided by 4, and that is true. So therefore P of n is true. For all n be a member of natural numbers, and that ends the proof. So this is a very interesting mathematical induction. Is very interesting and very simple. Just follow the steps and then you are there.